Hey guys, so for a recent paper that we wrote, I had to determine the complex refractive index of calcium zinc phosphide films, but this applies to any thin film. And the idea is to determine the attenuation coefficient of calcium zinc phosphide and the refractive index of calcium zinc phosphide. And we can do that through the transfer matrix method. How this works is you measure the amount of light that comes into the system, the amount of light that's reflected, and the amount of light that's transmitted. And from that, you can determine the calcium zinc phosphide complex refractive index. So actually writing out the equation for this, and the goal is to write out the equation for this and minimize that function to a value of the complex refractive index that leads to the measured transmission and reflection. So doing that can be quite complex. In fact, it becomes extremely complicated to do it by hand, and hence the transfer matrix method. Using the transfer matrix method, I'll talk about what that is and how we can use it in a second. But you can see that the calculated transmission, after minimizing our error, the calculated transmission and the measured transmission are quite similar, and the same thing for the reflection. So the transfer matrix method is a very elegant approach, and it breaks down this complex problem of a multi-layer system, transmission and reflection, into very nice looking math, and makes it very simple. So let's get to it. So just to define our goal, our refractive index is written as the real part plus some imaginary part. And what we're trying to find is the real part of the complex refractive index, both the real and the imaginary. And this has to do with the attenuation of the material. So how much of the light actually propagates through this transparent material. So in our system that we focused on in the paper, we had air, the film, the substrate, and we had air again. So we were trying to find N and K, not N star, but N and K, but individually for the film. So we write out this transfer matrix equation so that tells us light that's coming in, which we call En, is related to E out let's do this, E transmitted and E reflected somehow. So we determine what the reflected and transmitted light are through experiment of the system, and then we use that to determine N and K. How do we do that? The transfer matrix approach that we're going to be discussing in a second tells us the relationship between the incident light and the transmitted and reflected light. So that's the whole goal of the matrix transfer approach. So what this tells us is that E in is related to E out in this matrix called, we're going to call M. And I'm going to discuss this thoroughly in a second. But transmission, apparently, is 1 over the 1, index of the matrix squared, and reflection is M21 over M11 squared. And each of these M's contain, you guessed it, N and K. So if we minimize, we can't analytically solve it because it becomes very complicated, but we can minimize using our function or our error using the experimental values, and then we can find N and K. So let's discuss that. So let's quickly walk over the theory behind this. So say you have several layers of material or a system. So you have air, you have your film, you have a substrate, and then you have air again. So what happens to light when it comes through here is first, obviously some of it gets transmitted at this interface, and some of it gets reflected at this interface. And of this transmitted light, the light propagates through and then when it hits this interface, some of it gets reflected back, which propagates back, and then again, both gets transmitted and reflected back. So you see how complex it can get. So the idea is to have, let's say this is representing the light as an electromagnetic wave. Let's say this is the electromagnetic wave, or rather this is the electromagnetic wave in air, and it's going to the plus direction. So this being the plus direction and this being the minus direction. So let's say it's going in the plus direction. So A air going to the plus direction. So that would make this A air going in the minus direction. So, or air going in the minus direction, and this is going to be film going in the plus direction, and film in the minus direction, and so on and so forth. So our goal is to represent, is to have a function that has that, and a function that has E air 2 in the plus direction. So ideally what we're trying to determine is the reflected light and the transmitted light, and then from that we can determine the things like the attenuation coefficient of the film, and the substrate. The attenuation coefficient of the substrate is near 0, and we can determine the refractive index of the film. So let's do that. So we're actually going to represent this as, let's look at each interface individually, and we'll go over this quickly, but we want to have a matrix in which EA plus and EA minus are some interface matrix I, or I call it D in the code, some interface matrix multiplied by EF plus and EF minus. So this is the matrix that we're trying to find. So ideally, not ideally, but you can think of if you can write a function for EF, the transmitted light, EF plus, as EF plus is equal to, EF plus is going to be some transmission coefficient that we get from the Fresnel's equations, transmission coefficient multiplied by EA plus, so how much of this gets transmitted, and then plus, we said that some of this light gets reflected, so the EF minus gets reflected back, right? So it gets reflected back, and then comes here, gets reflected back again. So it's going to be a reflection coefficient, again from Fresnel's equations, times EF minus. And we can do the same thing for this guy right here. So EA minus is going to be equal to, so EA minus is going to be some transmission coefficient times EF minus plus some reflection of this guy, right? So EA plus. We can rearrange this and then write out our full matrix equation, and we see that I is going to be very elegantly 1 over the transmission matrix, or sorry, the transmission coefficient, 1 R, and then R, and then 1. So yeah, that's it. And so what we're going to do is we're going to find that interface matrices of this guy, and this guy, similar to this, again changing using the appropriate R and T, and after that we're gonna account for the propagation through each layer, so the propagation through the film and the propagation through the substrate, and this is how we find the attenuation coefficient of the film. So let's talk about the propagation matrix. So, but how that would work is I times the propagation matrix of the film, and then this other interface times the propagation matrix of the substrate, and then the final interface. And this would give us the light, light in is equal to this matrix that we're just going to term M times the light out. So by just looking at the light that's going in and the light that's going out, we can determine M, and from M we can determine the attenuation coefficient and the refractive index of the film. So what are these propagation matrices? So that is we can focus on just this film propagation for now. So let's write that out. So let's say the film is some thickness L from here to here, and we said we have the E film plus and E film minus, and here what I want to add is, I think that's the notation that we use, right? So let's call this point X and let's call this point X plus 1, X plus L. So this would be E film plus at X. And here we're going to have similarly E film minus and E film plus, but this is going to be at X plus L, X plus L. So each of these matrices, each of these, like E film X, for example, let's just focus on that, is the plane wave equation, right? If you, I guess I can, plane wave equation. So E to the I omega t minus k x, and E film X plus L, you see, would be E to the I omega t minus k x, or rather kx plus L. So if you work it out, you see that these two are actually the same, except for the coefficient of E to the minus I KL. So E f x plus is equal to E f x plus L plus multiplied by this. So if you work it out, you find that so our goal for the propagation matrix is to define EFX plus and EFX minus in terms of EFXL plus and EX plus L minus. It's to have some propagation matrix, and that's what we're trying to determine. So if you work it out, you're gonna if you do the algebra, or if you do the algebra, what you're going to find is P is equal to E to the I K L 0, 0, and then E to the minus I K L. Sorry for going through this quickly, but I'm going to put this on the notes, otherwise it's going to be very long, that's why. So at the end of the day, you're going to have each of these propagation matrices for the different layers through which you propagate, and you assemble that into this M matrix, and from M, essentially once you have M, you already know the reflected from experiment, so reflection from experiment, and you know the transmission from experiment, right? So what we're going to do is we're going to do a numerical solution for this, and we're going to try to find the values of N and K that essentially give us the experimental R and T. This is not a matrix, by the way, sorry, it's confusing. Okay, so now we can kind of talk about the actual code implementation. This is the data that we have. So this is the reflection, transmission, and absorption, and that's the energy of the material, or the energy at which we're measuring, sorry. And the code implementation, is I haven't found a very good like code implementation that walks you through on this, so I hope you find this helpful. But we're assuming a semi-infinite air layer at first. So let's see how this is. So there's the film interface matrix. There is the film propagation matrix, substrate film interface matrix, substrate propagation matrix, and substrate air interface matrix. So we assemble all of these together, and then we have our transfer matrix. So we can use that to, and I'm using a symbolic library, SymPy, to do this. So this is just converting the, and right here we're converting the energy into wavelengths, and assuming the thickness, well, we know the thickness of the film is around 460 nanometers. So after we assemble all of this, because it becomes quite complicated for a system with more than actually two layers, we have to numerically solve this. So how we do this is we lambdify the symbolic equation and then we numerically solve it. So I initially wrote my own numerical solver, but I think SymPy optimized is used much more in the public, so people will like this better. So we're using minimize from SymPy optimize, which I think is like the bare bones version. So we're solving for n and k, which is again the real and complex part of the refractive index, and or k is the attenuation coefficient, excuse me. So what we're gonna do, or what we did here, is we calculate R, the reflection and transmission, and then for our error, it's gonna be the difference between the calculated R and the actual, the calculated transmission and actual transmission, the calculated R and actual R. So just do the difference and square it, pretty basic. And this is our initial guess. For n, it's just 1, and for k, it's just 0.5, assuming there's some level of attenuation and typical n. So we minimize for this. This takes quite some time. So in this code, you can actually break it up into chunks of wavelengths if you just want to test it out. So this chunk of wavelength is from 860 to 940, and the jumps in the reflection is due to the interference pattern in the reflection is due to thin film interference. So you see that it's quite a good match, and the entire code is quite self-explanatory, and I hope you enjoy this video, and thank you.